Hi all, in this video I'm going to be showing how pi is approximated in modern times. So in the last video I showed how Archimedes approximated pi using polygons and increasing the number of sides circumscribed and inscribed to a circle, with which he arrived at this values, these lower and upper bounds here. And he got those are quite good values. And I showed how in modern notation we can write it this way, where n is equal to the number of sides, or generalizing or mirroring the bisect method that he used, we can write it like so, where I is a number of times the angle is bisected and n is the original number of sides. So the original number of sides he used was 6, so a hexagon, and it was bisected 4 times, so you end up with the 96 side. So how is pi calculated today? Well, for all practical purposes, Machin's formula, which he arrived at in 1706, is enough. And it's easily to calculate accurate digits into the hundreds and thousands using computers, using his formula. But 100 digits of pi would be more than enough for all physics problems on the quantum or cosmological scale. And now in modern times, the Chudnovsky algorithm is used, and it's used for trillion pi digit calculations. So really, it's just for bragging rights and to test computational power and see who can get the most pi digits. So, but how can you calculate pi without a calculator? Well, you use infinite series. So it breaks down into the basic arithmetic operations: addition, subtraction, multiplication, division. So for example, we have some quite well-known series here of sine, cosine, and Euler's number. Yeah, it's like I've said, it's a well-known series. But who discovered this series first? Well, historically it was astronomer and mathematician Milla L, and he was circa 1450 to 1550, wrote on the sine series discovered by Madhava. Other important series were also written in his work, so the cosine and arctan, and these were described via verse. And Madhava was an Indian mathematician and an astronomer. So in Nolakantha's work, the Tantra Sangraha, 2 important results are given along with the sine and cosine series. So written in modern notation, he arrived at the arctan, a series, and the pi series was also found. So pi over 4 is 1 minus over 1 over 3 plus 1 over 5 minus 1 over 7 plus, and that goes on. And that's quite an important series. And later on in Europe, the Scottish mathematician and astronomer James Gregory, he independently discovers the arctangent series in 1671. And Gottfried Wilhelm Leibniz, he independently discovers both the arctangent series and the series for pi, the infinite series for pi. And he did this by setting x is equal to 1 for the arctan. And Nilakantha, Gregory, and Leibniz, they all used different methods of proof to arrive at the results, although Gregory, he did not find the pi over 4 series, only the arctangent series, although some speculate that he did find the pi over 4 series, but because it's so slow to converge, he didn't bother writing about it. And here comes to the next point, where the problem with equation 2, or the pi over 4 series, is that the convergence is really slow. So you need to sum around 11, I think it's 10,500 or 10,600, or roughly around 11,000 terms to be accurate to like 4 decimal places. So the Archimedes method was much faster. So sometimes this shows that equations are elegant and beautiful, but they are not very practical. So Machin comes to the rescue. He was an English professor of astronomy from 1686 to 1751. In 1706, he found a way to calculate pi, which are much faster convergence. So equation 2 can be rewritten, and this is the Euler form. This is given in Sibbons' 1996 calculus textbook. Is pi over 4 is equal to arctan over 1/2 plus the arctan over 1/3. And by using the arctan series of equation 1 to calculate the two terms on the right hand side of 3, you can get a faster convergence. So equation 3 can be written because of the tangent addition formula, this here, which was known in Machin's time. So to just show how that is done, so we know that alpha is equal to 1, then the arctan is equal to pi over 4. So from the tan addition formula, we can let A is equal to arctan of the x and B equals to arctan of y. Now taking the tangent of that, we get this, but we know that the tan of the arctan is just equal to the x, or the input. So you take the arctan of both sides, you get this equation here. Now you can work out what x and y is, and so you let x is equal to 1/2 and y is equal to 1/3, and if we calculate that out, we get that it is equal to 1, so proving that x is equal to 1/2 and y is equal to 1/3. Now Machin, he used the following form. So he used pi over 4 is equal to 4 times arctan over 1/5 minus arctan of 1/239. So, and you can end up with this equation here. So, but why did he get the 1/5 and 1/239 terms? So Machin started with the angle, the 1/5, after some trials on what angle to use. And this, so it would be convenient for pen and paper calculations, and it would converge quite fast. So the following is how he did it. So from the diagram here, we've got the tangent line here, AD, the AD length, and its angle, which is 4/theta, and that is slightly larger than alpha, which is equal to pi over 4, or 45 degrees. Now this is the arc, this is the arc AK, so the arc of the circle here. Now arc AE is set up so that the length AB here is 1/5 of the radius of the circle, which is AM. Now the AF arc is 2 θ, and the AG arc, that is 4 θ. So thus the angle of the arc AG is a good approximation of the angle alpha, which is equal to pi over 4, or 45 degrees. And so knowing the tangent addition formulas, we can get the 4 θ, which is a good approximation of 45 degrees. So here we have the tan theta plus theta is just, that's equal to 2 θ. And we get this, so 2 times tan theta over 1 minus the tan theta times tan theta, so it's tan squared theta. And then for 4 θ, we get 2 times tan 2 θ over 1 minus tan squared 2 θ. Right? So we must find the angle of arc AF first, and then arc AG, which gives us a good approximation. So remembering that tan theta is equal to 1/5 of the radius, so tan 2 θ can be written as, we use the addition formula there. So that, and remember it's 1/5, so 2 times 1/5, and we get that, and we end up with a 5/12 here. Then with the 4 times the angle, we can do the same process again using this formula here, and we get 120/119. Now remember that this angle, it overshoots the angle that we want, which is pi over 4 or 45 degrees, or the arc AK. So that we must find the 4 θ minus pi over 4 to get that extra bit, and minus that from that equation. So we get the tan 4 theta minus pi over 4. We work that out, right? And we get this here. But that is just the arctan of 1 over 239 is just 4 theta over pi over 4. So that way we can work out pi over 4. So just remember that tan theta is equal to 1 over 5, and the arctan is equal to 1 over 5 and is equal to theta. Hence, we put that equation in there. We put that, that amount in there, and we get Machin's formula here. So in the next video, I might show how Machin did this with no calculator. And as you can see here, you just add up the series, add up the positive terms, and then you add up the negative terms, and you take those away from the positive terms, and then you times that by 4, and then you take away the series that you add up here to get your approximation of pi. He calculated 100 digits of pi using this method with just pen and paper in 1706, so that is no easy feat. But for an in-depth look at this procedure, see Ricky 2010, and I'll give references at the end of the video, but check out my next video and I'll go through, but I obviously won't be going through 100 digits because that will take a long time. But yeah, check out that next video that I'll make. So now, the dawn of the computing era, we had some major pi number crunching events, and some of these were using variations of Machin's formula. So in 1949, they used ENIAC to calculate pi to 2,037 digits, and that took the ENIAC around 70 hours. In 1961, they used IBM 7090. They calculated pi to 100,000 digits, and that took the machine 8.7 hours. In 1967, the CDC 6600 machine in France, they calculated pi to 500,000 digits, which is a credible feat. In 1989, there's the Chudnovsky Brothers, they calculated pi to 1 billion digits, so quite a lot. I don't know the time in hours of that, but they used IBM 3090. And in 1999, a team in Japan, they used a Hitachi SR8000 over MPP, and they got the digits to 206 billion before the new millennium. And that took 37 hours. But I'll just point out in the Shanks and Wrench paper, which Shanks and Wrench, they calculated pi to 100,000 digits using the IBM 7090 machine in 1961. They said such a theory, of course, could take years to develop. They were talking about new algorithms to increase or decrease the time of computation. They say in the meantime, say in 5 to 7 years, such a computer as we suggested above, 100 times as fast, 100 times as reliable, and with 10 times the memory, will no doubt become a reality. At that time, a computation of pi of 1 million digits will not be difficult. So, that's today's computing. Using my humble machine, which is has a 3600 Ryzen 3.6 gigahertz base clock. It has 16 gigabytes of RAM. I used it to calculate 1 million digits. And the Python program used is from a Craig Woods article. I've got the address here, and he goes into good detail about the Machin, the Arctan series and that, but he includes a Pi program in that. So I just used that, and it took, for 1 million digits on my machine, it took about, I think this 14 minutes basically. So it took about 14 minutes. So computation has come a long way, and silicon has come a long way. Now, the current record, as of this recording, was from the Google Cloud compute, and Iwao, I hope I pronounced that right, in 2022. And that they used a high memory 128 Ice Lake Xeon 2.6 to 3.1 gigahertz CPUs, and using 864 gigabytes of RAM. Now that took 148 days, and 515 terabytes of storage was used for that. But the team they used, well, it's almost always used, everyone uses the Chudnovsky Brothers algorithm. So this converges much quicker than any other algorithm, with around 14 decimal digits of pi per iteration. So this is the algorithm here, or the series. It's quite a hairy series, and not trivial to prove. But this was based off Ramanujan's pi formula that he gave. And Ramanujan was 1887 to 1920. And they got 100 trillion digits, which is just mind-boggling amount of digits. So I hope you found this insightful. Please consider liking the video and subscribing to my channel, and I'll give it some references here, but I'll include them in the description too, so you can have a look at them. So with that, thanks.